All right. Hi, everybody. I'm Stan Hu. I'm an engineering fellow at GitLab. I've been here for about close to 7 years now. And today I'm going to talk about um, Prometheus client-mmap gem. mmap stands for memory map, and we'll talk about why that's the case. But before I get too deep into those details, I'm going to give you a background about the motivation for this talk. I realized that someone submitted a bug for this gem, and I realized that there's not a lot of the people in the company who have worked with this gem, and it's a critical part of our infrastructure right now because we're relying on it to monitor GitLab.com today. So all those metrics you see on our Ruby dashboards and things like that, it's really supported by this gem. And I think about the XKCD comic on the right, where there's one poor person in the open source world supporting this giant behemoth. So in this case, this behemoth at the top is GitLab.com, and all customers using GitLab, and that one little pylon is this little gem that's being used quite a bit. Oh, it's just someone's in the waiting room. And on the left, I feel like I'm just trying to increase the bus factor here and just get more knowledge about this gem and how it works. So I'm going to delve into the details. But first, we see these nice dashboards. If you go to dashboards at gitlab.net, I believe, you can pull up different dashboards relating to Rails, Sidekick, all those things. And those metrics primarily come from Prometheus. And we have a lot of Prometheus servers that talk to our Puma workers, our Sidekick workers, and they scrape them through HTTP endpoints. And this is where we get all this data. And you can see in this dashboard, at the top here is a controller, and you can change different controllers, different actions, and so forth. So all that comes from these Prometheus metrics, from this gem specifically. In Prometheus, there's really four main types of metrics. There's the counter, which is just like a running counter from 0 to infinite, and then there's a gauge, which is like it's just a single number that changes from for example, how many pending jobs are there, and that will fluctuate from 0 to 1,000 and so forth. Histogram is like a bucket. Is if you care about like you want to bucket like the response rate, for example, like the request time. Let's say you wanted to know whether something was under a second or under a half second. You might use a histogram to kind of figure out where your samples lie in this histogram. In some ways similar to histogram, but for the most part, it isn't being used because histogram is more useful and better supported. So I won't talk too much about that. If you ever find yourself trying to look at some Prometheus metrics on a process, this is an example from a Go process. It's an HTTP endpoint. You can just curl it with in this case, I think it was a Redis exporter, but really the standard in Prometheus is to add /metrics or something to the end of this URL. And you can see it's mostly plain text. And this is a good example of the three different types of Prometheus metrics that I talked about earlier. Histogram is here. You can see this is I think this is the Go garbage collection, how long it took. And generally you want the smaller, so that there's different buckets here. This is the quantile is I think the number of seconds it took. So, for the most part, things took under 0.25 seconds and so forth. And there's a gauge here, it tells you the number of Go routines running. And then this is the counter. This is an example of a counter. It's just the total number of bytes that were allocated throughout the history of this program. But then, going back to Puma and things like Sidekick, which run multiple processes to support, web applications, multiple processes really add some complications here, because if you think about how so on the right, we have the Prometheus server that's trying to scrape for metrics. And let's say you have 4 Puma workers and you have, like, say, spread across 10 different machines, right? So you're starting talking about, 40 different processes that you need to scrape. Well, how do you do that effectively? You have, let's say you wanted to total the number of successful responses across my entire fleet. Well, there's a couple ways to approach that, right? So one way you approach that is to, just add one port per process, right? It's simple to understand, but then suddenly, as we mentioned earlier, you're starting to talk about hundreds of ports that you have to open, and then the scraper has to be aware that, oh, I need to talk to these, all for every process I launch, I have to talk to a different port, and it's easy to miss one, right? So you can see that it starts to get a little complicated when you start to scale up your fleet. The second approach, which this is what we do today, is make the application deal with it, right? Try to hide the fact that you have 10 processes and just expose one endpoint, and the Prometheus server can scrape just one endpoint, and the application can deal with aggregating from multiple processes. The downside is things get a little more complex for the application. We'll talk more about that. And you also have to be considerate of performance as well, because now you're dealing with aggregating samples from potentially tens of other processes. And the third approach, which I think other software processes are doing today, is just avoid multiple processes in general, right? Go does this really well, where you have lightweight threads, Go routines, and things like that. So you can run a single process and it can farm out to different cores effectively. And when you scrape the data, you really need to just talk to one process, right? The problem is we have a lot of things already, like Puma and Sidekick, that really do need to use multiple processes today, and rewriting it not to do it would be extremely expensive. So in a lot of cases, this is just not really an option, because you don't want to redo your entire stack. So when we first started this effort to measure GitLab.com, we implemented something mostly in Ruby, just to see like how effective this could be. And I think the first efforts was that it didn't work very well, because we had so many metrics on GitLab.com. We measure every HTTP request, what action it was, which controller it hit, how long it took, how many database calls or Redis calls, all those things we measure. And you start to think about how many metrics we start to have, and just with I think this first test is that we had 50,000 metric entries. It took 5 seconds to aggregate them. So when someone scraped the endpoint, it would take 5 seconds for on a local MacBook to just get all that data, and that just got worse the more metrics you added and the more processes you dealt with. So that wasn't going to fly, right, just on this local test. So there were a couple ideas. Well, how do we make this faster? And the first idea is really important in terms of aggregating data from multiple processes, is to use some memory map files. And that's where the mmap name comes from. Mmap is a system call in Linux that allows you to open a file and then map it into user space and treat a file as though it's almost like just memory. So I'll talk more about that in the next slides. And the second idea is to do more of the heavy lifting in C code. And that's sort of where, this is sort of where this gem was born. So mmap in a nutshell. So if you ever want to access data in a very efficient way, you might use mmap. And there are some cases where it works well, and there are other cases where it's not worth the complexity. But in this case, I think it works really well, because let's say you had a file on disk. Well, this is how it works. You would open the file, and then you would call mmap to say, hey, can you map this file that I just opened to some memory region? So now whenever I want to read and write to the file, instead of doing explicit file read or file write calls, I'll just manipulate the memory, and the Linux kernel will deal with all the details about reading data and flushing it to disk. There's more detail. There's a great YouTube video about how this works in Python. It's applicable to here also. But where it really shines is with multiple processes, right? Because as I talked earlier, we have this problem where we have tens of workers, and really we want to be able to read data from the same workers if they're on the same machine. And so the nice thing, so Prometheus metrics really lend itself to this pattern, because let's say I want to update a metric, right? I may need to write to a random part of a file, or read from that for that matter. And sometimes we just can't predict like where we're going to read or write. So the metrics can be pretty random. And memory maps are generally faster for random access. There's a flag when you call this mmap function called map shared, and that's really saying I want to share this memory with other processes, right? So let's say I have 5 Puma workers. If they all memory map to the same file, the kernel will know that, and they'll all essentially be able to look at this and manipulate the same memory and get the same results. And so it's a nice way of doing inter-process communication, right? So now I don't have to worry about well, if worker 1 writes this data, how is worker 5 also going to see that, right? And that's really where this idea is really powerful. And so this is kind of where a prometheus-client-mmap, this gem, was born. There were some low-level routines originally created by Aaron Patterson. It's a C extension. It's pretty hairy, but it hides a lot of the complexity of using mmap. We had hired Kevin Leiduff to work on Prometheus instrumentation for GitLab, and he took this gem and updated it for the latest Rubies and called it mmap2. And in March 2017, Kevin and Pavel, both of whom are no longer part of the company, they forked the upstream Prometheus client to add in mmap2. And so Prometheus client mmap is sort of a hybrid of the original mmap gem and the Prometheus client and mmap. And so at the time, the Prometheus client gem didn't have support for multiple processes in Ruby. There was a lot of discussions about how to approach it. And today they have support, but I'll get to how it's different from what we're doing here. But that's 5 or 6 years ago, so it's been some time. So to get into the details of how mmap is being used by this gem, well, this is a simplified C code. There's if you want to actually look at the actual invitation, there's a link there. But essentially, as I mentioned earlier, is on line 12, where you open a file. Let's say it's like temp something db. In this case, I'm opening it only for read only. And in the case of the gem, it actually will create the file that doesn't exist and make it a page size so that it can be memory mapped. And line 17, you get the size of the file just to see, like, well, is it how much memory I need to actually map. And then line 22 is where we actually do the magic, where we are mapping this file descriptor, and you get back a pointer and see that a pointer is basically an address to an address to memory, right? So now if I want to read or write to that file, I can now just, like I said, treat it like memory. I'll get to we can talk more about the details later on, but essentially now I have a pointer which I can manipulate to my liking. I can assign it characters or whatever, and then it magically appears on disk. The Ruby code looks a lot more straightforward here. There's a registry that holds all the types of Prometheus metrics that you first get. And then once you have the registry, you say, okay, let's say I want a counter of all the HTTP requests. I just say, I want a counter. HTTP request is the name of the metric, and then this is the description. And then if you want to start incrementing, you just call it increment. Very straightforward, right? How it looks in the Prometheus client mmap. Well, as I mentioned, there's this registry which has certain types registered. In this case, is the counter. And this is where the details are interesting here. A counter is a type of metric. We've modified it to include this uses value type because we wanted to be able to define our own definition of what a Prometheus metric, how it's implemented. And so this mmap values, which holds a lot of the logic of how to actually turn a counter into something that's stored in a memory map file. So if you look at any Puma worker today, you might see it has open files to something called like counter_Puma, gauge_Puma. And these are just 3 different memory map file per counter per metric type. And so each process should have a different file name. So in this case, Puma 1 there might be Puma 2, 3, 4, and so forth. So mmap value has an instance to mmap file. And mmap file is a subclass of mmap file. You can click on that link to see the actual implementation, but mmap file is really just all C. It's a Ruby class that's all implemented in C. And the main routines are in mmap C and value access C. And we'll delve into some of the details. I won't get into too many, into all of them, but I'll highlight some of the important things. But before we do that, I mentioned that there's these .db files. This is how the metrics are actually stored on disk. This is the byte layout. And I want to point out that the first 4 bytes of this file is the total number of bytes used by the file itself. This is important because it's going to be used to figure out if I need to append a new key to my database. I can just seek to the point the number of used bytes. So let's say there's 20 used bytes already in this file. I'll just seek to the end of the file and just start writing data here, and that allows me to just add entries very easily. And that's padded to an 8-byte. Yeah. And so it's a pretty straightforward structure. Let's say a key is basically every entry here is a metric, so it stores as a key value pair. So I should actually say value 1 here, but so in this green slide here is the number of bytes that the key name holds. So let's say, I'll go to an example here. Let's say the key name is GitLab transaction cache read miss count total, right? So the size will be the string length of that, and then we actually store a bunch of other things, including well, and in Prometheus metrics, there's a notion called labels, right? So labels allow you to add more context to your metric. So for example, if you wanted to label this with the action, the get request, right? So that would be the get API jobs in this case, or the controller or the feature category. All that stuff is all those things are in labels and they're serialized in this form. So if we go back to the slide, basically we can add a variable length key values here, but the value itself is always 8 bytes. It's a double, right? So this allows you to have as long a string length as you want, right? As long as it fits within a 4-byte size. So that's should be plenty of bytes for a string. In this case, when I was looking at this yesterday, I was like, why is there a metric name and name? Well, it turns out it's just redundant. I'm not sure why it was added, but I think in the future it could probably be dropped because I don't think they're being used. These two different names are being used. If you actually want to look at these DB files, you can do that with a convenient bin parse function in this repository. And here I just run bin parse and -t is to show the text form. And in GitLab, all these DB files are stored, or at least on the omnibus, they're stored in /run/GitLab, and that's defined by this Prometheus multiprocessor environment variable. So if you ever wonder where these metrics are being stored, look for this environment variable or define it yourself. I think if it's not defined, it ends up just being in the temporary directory. And you can see that it's, you see the name of the metric here, the different labels, and then the actual value is here. So that's just if you ever are curious, you can take a look at it. So how does it work when you actually increment a counter in the Ruby? Going back to this whole like, hey, I just incremented a value here, right? Well, there's a lot of details that go into behind the scenes, right? So when you increment the counter by 1, it calls the mmap value increment. The first thing it does is figure out, hey, did my process ID actually change? And if so, this is where it does the logic of opening a file and then memory mapping it, right? And then internally, it will increment the value. So internally, it stores what value this counter is in memory in this value, and then it increments it. And then after that, it then needs to actually write this to disk, right? So it's almost like it's committing the actual value to disk, and that's where it's really persisting. So you have a key and a value that you want to persist. This mmap dictionary gets called write value, and then this calls is upsert entry, and then this is where the meat of this process happens in the method upsert entry, and this is all C code. So let's look at that C code. And for those who haven't looked at C code, I'll walk you through it. This is not as scary as it looks. This upsert entry, the first 2 lines are just check type. This is a Ruby call, Ruby C extension call, just making sure that positions is a hash. It's just a hash of the values in here, right? So let's say I have key, let's say I have the GitLab cache misses total. This positions hash will actually hold that key to the offset in the file. So if I know the offset is say 20, like let's say offset is here, it will just hold the offset, all the different offsets for each key. So it'll know exactly where it needs to write in memory. So that's just making sure it's a hash. The key is a string, right? It's a Ruby string. So that just, it will just, this function will return invalid if none of those things aren't true. This next lines are just, there's some internal structure for managing the memory map. So that's what this get mmap structure is. There's self is the actual object that called it. In this case, it's the mmap. I think it's the mmap file here. So it's just getting this data structure from the actual Ruby object. Again, this is all C extension stuff. So essentially it's doing Ruby-like calls here. Everything in Ruby is basically can be translated to C code here. So this is where it actually does the lookup of the key. So let's say I had the cache misses key, I'll find the offset. And if that position is already there, like that entry is already there, it's just going to go save the value directly in memory, and then return whatever value it saved out. And then if it doesn't exist, then it creates a new entry and appends it to that file, and then again reads out the value to make sure it got it right. Any questions so far?
I sort of want to like reiterate what you were just saying to make sure I understand. There's a lot of content there so far. Yeah. So let's say I've got a single server with a single Puma primary process. Now, the old way of doing things is that the Puma primary process may fork, let's say, 2 worker processes. Yeah. And then each of those worker processes would bind to an open port. And then Prometheus itself would query each of those open ports to collect the metrics for each one. Each of those processes would then collect their memory and write it to disk in the event that the process would go down. Is that right? This is before mmap. This is before mmap, right?
Before mmap, it would.
So like it's collecting metrics and it's storing it in memory in each process, right? Mm-hmm. And so that means like Prometheus has to query each individual process on the specific port. So the value that this adds is that it creates a temporary file system or in-memory file system. And then when each of those worker processes starts up, it will attempt to open a file based on the process ID of that worker process. Correct. In that in-memory file system. And then from there, the part that I didn't understand is how the IPC works. So is Prometheus now like reading directly from those the memory map files, or is it going to the primary process to still aggregate?
So you know, if you have 4 different workers, right? Any of those workers could be scraped by Prometheus, right? So it depends. Let's say 3 of the workers are busy, and then Prometheus comes along and talks to the 4th worker, right? So to get all the metrics. You're actually alluding to the next part about marshaling it. So what happens when you actually, when the Prometheus server scrapes one of those workers, it's actually going to look at this multiprocess files directory and try to find all the .db files in that directory, and then try to read out all those .db files.
So based on the convention of the file name process ID, yes, we can just scrape the data directly from the yes, memory mapped files, as opposed to going to the process to ask for that information.
Exactly. So we just read out those .db files because each process is basically just updating those for its own process ID. And then if you just read them all out, and you can aggregate it from there.
And then because this is a single DB file per process, if there's multiple threads in the process, is there like locking or contention that needs to occur to make sure when we're incrementing the value of counter?
Yeah, so I mean, each thread should have its, well, depending on what it is, there's a lot of locking. If you look at the code, there's a lot of synchronization around it.
Okay, and that's in the
So yeah,
C.
yeah, that's all in the, it's all in the, I think a lot of it's in the Ruby code actually. So there's a lot of mutex and synchronize and all that. So that's a good question. All right, so I'll back up. Any other questions regarding this? So this on line 213, you see this initialize entry. Well, what does this do? So this is actually gets into the details of how memory mmap really works. You know, the first couple lines are just making sure that the memory map isn't frozen. You can freeze the memory so people can't manipulate it. So there's an error, an exception gets thrown if that happens. If the length of the key exceeds 4 bytes or 32 bits, right? You also get an error here. And that's why, you know, I mentioned it has to fit within that range. So in the next 169, 165, 160, you know, 174 is where a lot of the meat happens of the updating here, right? So we know we need to figure out the length of the actual key that we're going to store here, and that's doing the string length here. And here's the offset, right? So we know that, let's say the string is like 50 bytes, right? We want to pad it out to an even 8 bytes, right? 8 byte aligned system. So that's the padding length. And then the total entry length on 167 is that total plus the size of a double. So a double is 8 bytes generally, right? In the floating point. So that's your total entry length for a single metric. Now, on the 169 is the lows used. Basically, it's reading from that used value up in here, right? This first 4 bytes of this structure, right? And so this is where memory mapping is kind of cool, because now in order to find that used byte, I don't need to tell the file system seek to the beginning of the file, read it out, right? I can just say, just give me, you know, I'm gonna actually access that first those first 4 bytes directly, and that's my used counter, right? So now if I notice, hey, the total length is actually large, is if it's under how much data I already have, so use plus entry length, right? That's basically what my new total is going to be. Then I'm sorry, if it's all right. So if my total length is if my memory is, if my DB file is not big enough right now to accommodate this new metric, I need to expand it, right? So the way it does it is it doubles the buffer here, and that's what the expand does, right? And so expand actually calls mmap again to say, hey, I need a bigger buffer, right? And so that's what happens. And then once we've got a big enough buffer, I'll save the entry in here. And then I'll update the used value. Oops, I'll update the used value to reflect that I've just added this entry. And then 179 is actually setting the hash, the positions. It's basically doing positions, you know, key equals my new offset, right? So you can begin to see where, like, there's a lot of pointer arithmetic happening here. And if you haven't worked with C pointers, it's okay. It's just manipulating bytes in memory. And I don't know if you can do this in Ruby as effectively, but essentially it's the same idea, is basically updating data in this data structure as efficiently as possible, right? So, and because we're just copying stuff into memory, you know, the mmap automatically handles flushing that data to disk. So we touched on about, like, well, how do metrics now get marshaled? So when a Prometheus server comes along and says, I want to give me all your metrics, right? You'll see this call in our GitLab server. It's a Marshal multiprocess, and you give it a path. This path is where all these .db files resides, right? By default, it just uses whatever was configured. And so let's look at this magic 2metrics implementation, right? So I'll give you some background. 2metrics was implemented in this merge request. It's implemented all in C. Originally, it took 27 seconds to render a lot of this data, and then suddenly with this change, it became 100 milliseconds. And so the main optimizations is essentially implemented in C, right? Using efficient JSON parser, and then using a low-level C hash, hash map and hash set. So it's actually quite an elegant function. If you look at it, you couldn't, you wouldn't think that it's that complicated here, and it really isn't. It's using basically its own hash map on line 64, and then it's taking aggregate files, basically takes that entire file list and tries to read every metric and store it into this hash in this hash map here. And then line 74, it sorts it, and then 80, and then once it's got all those entries sorted in this map, it will then create a giant string to send out to the buffer, right? And then just cleans up after itself. And so with this C implementation, we get this massive, 270x speed up. So it's a really nice implementation. And I think where this is relevant is I think there were some attempts to implement a Go version of the exporter. And even with the Go version, it wasn't able to efficiently marshal all these metrics because of memory usage, garbage collection, and all that. So this might be a case where C really shines because you can do a lot of this stuff in a much faster and less memory intensive way. So, all that being said, what could be improved here? So, the problem with C extensions and mmap is that it's very tricky to get right. We had a lot of crashes, a lot of bugs when this first rolled out. It took us, I would say, nearly a year to get this stable because we had a lot of core dumps and things like that happened in production, and it was really painful. And then more recently, Matthias from the application performance team discovered this really hairy bug. He was trying to inspect the entire heap of all the strings, and as he noticed that he was causing seg faults in the Ruby interpreter when he did that. Well, turns out that yeah, it was a hairy bug, and we eventually fixed it. But there, that pointed out to the problem was we didn't have a lot of knowledge internally about who could fix this. So this is hence this talk. As I mentioned, there was an upstream Prometheus client. We would love to switch to it, but right now, at the scale we're running at GitLab.com, it probably would require using a temporary file system because it doesn't have these mmap optimizations. And even then, I'm not sure that performance, both in terms of speed, CPU time, and memory usage, is good enough. So this is why Mo and I have started talking about this. Is there might be an opportunity here to kind of take what we've learned here and port it to Rust because there's a lot more buy-in in Rust and a lot more type safety and maintenance improvements that we can get because the Ruby community has already adopted Rust for YJIT and things like that. And if we can upstream the changes, I think it would be even more powerful because the more eyeballs, more help would be really useful. And so this issue on C is basically talking about the original problem that they were trying to solve. So I encourage you to read that if you want to know more. This is the current landscape. I won't get too into details of these, but there's other, since we've started, there's been other solutions that try to address the multiprocess problems. They all have their pros and cons. I think what we're doing with prometheus-client-mmap works well for what we're doing today, but it was a huge engineering effort to get right. And we need to get it to a state where it can be maintained by more people. I just want to highlight some of the differences between the upstream client. We generate, as you saw, one file per metric type, but in the upstream client, they actually generate one file per metric. So if you imagine we have 50,000 metrics, that could be 50,000 files times the number of processes you're running. It's a lot. The API is very similar because we did fork it, but there are some differences. So performance is the biggest thing, right? When we did some benchmarking, we noticed that there was a lot of time spent reading and seeking within their own binary representation. And this is why we think that the temporary file system may be required if we ever want to use it. But the plus side is they're using Ruby only, so it's a lot easier to maintain and test. And whereas we're using this hairy C and C extension and memory map trickery. So, any other questions? Let's go over to the discussion.
I have another question I didn't put in the doc here, but it was related to the function that was generating the method to metrics function. when I look at that, is that like the equivalent of calling the /metrics endpoint where it's generating the, okay.
Yes,
And
that's exactly what's called when, if you look at GitLab implementation, that is exactly what it's called when you do the /metrics endpoint.
And I think I may have made a mistake mentally, but like the memory map file, when I'm in a process and I open up an mmap file, that file is in memory, but it's in process memory. So it's isolated to just that process, right?
Yes.
Okay.
Yes. And so you had a question about open telemetry. I want to reiterate that. Does it? Yes, it's definitely relevant to that. But I think there are two parts to that question. Is that one of which is like, well, how are they doing metrics gathering? Right? They have a bunch of SDKs, just like the Prometheus client is an SDK to gather these metrics. I think they're still in development. It looks like they have some basic things like counters and gauges and things like that, but I don't think they've tackled how you handle multiple processes yet. I think it makes sense because it's a little bit of a niche problem, but it's also a much more complicated problem, as I mentioned. And the second thing is like, well, what do you do with the data once you get it out, exporter format, right? Once you want to export this data, what do you do with it? And it sounds like open telemetry is designed to work with Prometheus metrics. There's a lot of talk in that link about, how to deal with, counters and gauges, Prometheus and things like that. So I'm guessing they're trying to be as, compatible as possible because Prometheus sort of become the de facto standard for telemetry today. So I think that as long as we're doing things well with Prometheus, we should be able to interact and interoperate with the open telemetry pretty well. I don't see any need for us to switch to their SDKs right away.
I think the premise of the question was more about like the push versus pull of metrics, where it's like we're pulling metrics from each process versus the process writing to a central location where an exporter could then push it. And so I just vaguely recall going through some of that in
yeah, that's definitely that, and that's what and the different solutions are also trying to approach it that way too. So like and can you see the slide right now? Is this
see the 4 options?
Yeah, so I would say options in 2 and 3 are more push models. StatsD is a number 3 option. StatsD is a way of, a lot of software does is where they have a software that just pushes out UDB metrics, and there's they'll push out to something that's listening for it, and that could be a StatsD exporter that's a Go process. It could be something else, but basically it's fire forget, right? The application just sends them out, and whether they arrive, you never know. And that's a similar approach to Sam Saffron's approach with Prometheus exporter. There's a separate thread, and it just will keep data in the memory, and then occasionally just send this data out to this over a socket, and something has to scrape that exporter too. So it's kind of a hybrid. So yeah, there is a fundamental philosophy. Like Prometheus has been very much pull as opposed to push. But both models can work.
And then the risk, I guess, in both models is like if the process owns the metrics, if the process crashes, then we potentially lose that data.
Yeah, that's correct. Yeah. But generally with metrics, if you're scraping regularly, you get them regularly, it's good enough.
And so that C code for generating the metrics was important because we're not putting pressure on the garbage collector because we're allocating exactly enough memory to provide a response. So the Prometheus.
That's exactly right. That's exactly right. And there was a lot of, if you look at the profile, there was a lot of overhead with JSON, right? So there's a lot of hash map, a lot of getting data out, reading keys, and things like that. And so I think using the C implementation was much more efficient because there wasn't so much, so many string allocations and things like that.
And that's why something like Rust may actually work well because it's got the sort of type safety, but we don't have the overhead of a garbage collector having to clean things up. And we can allocate exactly the memory that we need and nothing more.
Exactly. So that may be the first thing to kind of validate is like, can we aggregate tens of thousands of metrics really efficiently in that manner, right? I think, like I said, there was a separate Go process. I think the GitLab metrics exporter that tried to do this in Go, and you can talk to Matthias about issues he ran into. I think basically he found that it just wasn't fast enough.
And so that'd be like a sidecar process operating on the same container or server that's collecting the data, as opposed to in process, which is what that's what this does.
Right. It could be, like I said, yeah, exactly. It could be a separate process if we wanted it to.
But we don't need that overhead if we can do it in
Yeah.
process.
If you can make it within the, so what's nice about this gem is that everything's in the same process, right? You don't need a separate process to think about, if unfortunately that also ties in reliability issues, right? If we get a seg fault in the instrumentation, then we also bring down the web application server. So there is a downside to that, but there's also a plus sign in the sense that there's not another component you have to worry about.
And I've got one more question. There was a picture, like a stick person picture with the bus. Who is that person, Stan? Just curious.
I'm taking it to be me at the moment because
you?
there aren't a lot of people working on this gem. There are surely other people in this company who can pick it up if need be, but right now I feel a little bit like that.
Okay, so we want to save Stan, right? Because
we want to save anybody who knows anything about this gem, right?
You could probably point out that the bus is also doing a pretty sick wheelie, so that's kind of cool.
Yeah, are you driving it, Dan?
No, I doubt it.
Okay.
I'd be too scared to do wheelies.
Great, so thanks for that. Yeah, using the upstream client, I think that's. Can you speak to how many metrics you have and sort of what your experience has been with that?
Hi, Stan. Thank you very much for this presentation. Yeah, I just added this comment here. I forgot to put my name. I don't have much to say about the metrics here. I just want to say that, the customers dot project is like a much smaller project than GitLab, and we started creating metrics for this project just over the past year, right? So we sort of like started fresh. But since you brought up that that client into your presentation, I was thinking of just I thought it would be interesting to just maybe as a follow-up for those who are interested to have this the project the customers of project here on the Google Doc. If anyone want to
yeah, thanks for that. I'd be curious how many metrics you're sharing. Are you using the direct file store implementation?
Store, that's the one. Yeah. That's the only type of store that you can use in like a clustered environment.
Mm-hmm. Okay.
And as you've highlighted in one of your slides, maybe like the second from last slide, you do have one file per process per metric. Yeah. You see that? That's
So yeah, I'm kind of curious how many files you generally have like at a given time.
At a given time. So I think I checked staging, but yeah, but like on staging, for example, it would be something like 20 files because we have like what three Puma workers, sidekicks. We have like a max of 5 workers for sidekick, but really sidekick is not the bottleneck for customers dot. So we have like 2 or 3 workers like running, and then we have I don't remember how many metrics, but anyway, I just checked on staging. We have like 28 files.
Okay, that sounds pretty nice.
Yeah.
Does that mean you don't have that many metrics right now?
No, we don't have that many metrics. We have 4 counters, and funnily enough, I just started work a few hours ago in introducing the first gauge. Okay. So yeah, that's.
But you're not talking about thousands right now. So right, I mean, we're talking about thousands.
As I said earlier, it's not the same scale.
Yeah. Okay. So the upstream client makes perfect sense in your use case. I think our hesitation is switching right now. Everything may just fall over, and so there's a real hesitancy to kind of switch over right now because our initial benchmarks show it's much slower than what we're doing today.
Yeah.
James, sorry to interrupt. Jesse, were you going to ask a question? I didn't mean to cut you off.
I was going to kind of follow up on what Stan just said, but if you're doing the same, then go for it.
Yeah, I always had a different question, so go ahead.
Yeah, I was going to ask about that comment on, switching to upstream. I mean, have there been efforts to contribute to the Prometheus client, like kind of incorporate I was just actually looking through the Prometheus client issues, and there are people in there complaining about performance. I'm sure there are some other people in the world who are unaware that we have our own implementation that I assume they could use. If I haven't checked if it's public or private.
Yeah, so actually some people have already used it, but I think it's a niche number of people. I do see random issues being filed from people from time to time, but you're right. And this is part of that's a good question, because this is part of that discussion right now, because Mo and I started talking about, well, how can we make that upstream version much faster? And one of the ideas was let's use Rust. Let's take what we've learned here, use Rust and try to upstream all that and just show people like this is going to be much faster, much more efficient, and then start switching to it, right? And if we can do that, I think we'll be in a good position to upstream things. Because this is sort of the beginning of that effort.
And the GitLab customers project might be a great place to do like the drop-in replacement if we can get a version that's API compatible, but also has the performance tuning improvements of the gem that we currently have.
Are you, sorry, sort of vaguely related question, is anyone from GitLab a maintainer in the project for the Prometheus client?
And the upstream, I don't, well, it's possible I have access because I'm part of the Prometheus group, so I might have merge access just by the virtue of being in that group, but nobody, I think, internally at GitLab has actually contributed to that upstream library yet. I could be wrong though.
Yeah, I just think that's one of the patterns we've seen with these separate projects where we fork things and we want to start contributing back or continue to contribute back, is to get maintainers in there and reviewers, and so show that we're actually contributing to the project.
Right.
Not an easy thing to do necessarily, though. Not suggesting that it is.
Yeah, I mean, I think if customer.com is using this, then I think if there's issues, I think there's a lot of interest in fixing them. So, but I don't think they're hitting the kind of problems that we might hit at scale yet. So. So I think, yeah, I think if anyone's interested, I think Mo and I are going to start looking at like, what can we do next to kind of move forward so that we can maybe tackle some rusts, some things. So if you're interested, let us know. We'll be happy to discuss. All right, any other questions?
And thanks so much. The crowd goes wild.
Like, I appreciate the time you took here, Stan. That was interesting, and great work on the hype there, Mo. That was excellent. Excellent.
I paid him to be my cheerleader. Thanks, Mo.
I think that should be an official position at GitLab, though. I don't think you get cheered enough, Stan, but thank you very much.
Thanks, everyone. Thanks, Dan.